All right, last week we became experts at using Boyle's law and Charles' law. Boyle dealing with volume and pressure, PV equals K. Charles dealing with temperature and pressure, V over T equals K. Notice you multiply by pressure, you divide by temperature. And then we looked at the V1, T1 thing and all that. So today let's look at two other gas laws. The next one is kind of an alternate form of Charles' law, but often, if you remember, we kind of said that Gay-Lussac also did the Charles' law thing. So really, Charles and Gay-Lussac both did the law we learned last week and the law we're doing today. So often the law from last week we call Charles' law, and this new one we call Gay-Lussac's law. Whatever, we gotta give them each credit for something. So remember, Charles said if you heat the gas up, the volume will expand, assuming you're holding the pressure constant, like in a balloon. But what if instead you don't hold the pressure constant, you let the pressure change and you hold the volume constant? So now instead of using a balloon that can expand, we're going to use like a sealed canister, like a steel canister that is not going to expand or contract. And then we'll look at what happens to the pressure in the gas as we change the temperature. Another good example of that is the pressure in your tires of your car. So they don't really expand or contract much. Instead, the pressure grows and shrinks. Now, you'll notice based on just everyday experience, the pressure increases with temperature increase. So they're directly proportional. As the temperature goes up, the pressure goes up as well. So notice you take your tire pressure, and then in the winter the temperature gets lower, the pressure in your tires gets lower, and you get those tire pressure alerts and you got to put more air in. In the summer it gets hotter, temperature rises, so the pressure in your tires rises as well. It's why you're not supposed to heat up gas canisters. Take maybe even like a spray bottle. There's a gas in there that's used to produce the pressure that sprays the stuff out. It's at room temperature, so it's at whatever pressure is in there, just enough to spray the liquid out. But what if you take it and you do something totally stupid and throw it in a fire? Don't try this at home. You will get hurt. The temperature gets larger as it heats up. Now, since the volume's held constant, that means this law applies. The pressure gets bigger. And now you put it in a fire, so it gets really, really hot. The pressure gets really, really large enough that the thin-walled metal container can't hold it anymore. And so the gas pressure pushes through the container ruptures, and you get an explosion that throws out expanding, steaming hot gas and little pieces of the metal canister. So you want flaming hot shrapnel in your face? Go try it, I guess, but I don't recommend it. But notice this Gay-Lussac's law, pressure is directly proportional to temperature, or P equals KT. Rearrange, solve for K, P over T. So you get P1 over T1 equals P2 over T2. Now, so that's tying in, again, all the gas laws. Notice pressure, volume, and temperature can all interrelate through those three laws. We now related each one to the other. I want to do more with that, but for the moment, I want to go up to one last gas law, and that's Avogadro's law. Everyone else is having a good time dealing with, what if I change pressure and volume? What if I change temperature and pressure? Whatever. And then Avogadro comes poking his head in and says, hey, what if we throw moles into that? Because that's his thing. He loves moles. That's all he wants to talk about. Ruins the party, right? But what if we do throw moles into it? Well, remember, as we've been going through all these gas laws, we've been saying you have to hold the amount of gas constant. Boyle's law, we wanted volume and pressure. We had to hold temperature constant and the amount of gas constant. Don't let any gas in or out. Well, what do we mean by amount of gas, though? We don't mean volume, because that's expanding and contracting. Maybe it's the mass of the gas. You know, how many grams are in there. That'll work for measuring the amount of gas, but the problem there is it's not universal. For all these other gas laws, they apply no matter what the gas is. Could be hydrogen gas, could be mustard gas. Doesn't matter. They're going to behave the same way and follow the same exact gas laws. If you go by mass, they won't, because some molecules are heavier than others. So Avogadro realized, well, maybe we should go by moles. And if we do that, then it does behave like the other gas laws, and it works the same no matter how heavy the molecules are, because the moles factors out the masses. So when you do that, you get the obvious result. The more gas you put in there, the more volume you're going to have, assuming you don't change the pressure and the temperature, right? So as you pump air into a balloon, the volume expands, strangely enough. Mathematically, volume is proportional to number of moles. You can do a gas law similar to these, V equals Kn, so V1 over N1 equals V2 over N2. We're not going to do much with that, if anything at all, because it's not a real common thing to have to worry about. But just be aware it's there. If we had more time, we would actually play around with it a little more. But this is the last 2 weeks of instruction we have here. The final week of school, the third week, is just make-up time. So the end is near, right? So let me leave the slideshow and go to my whiteboard and maybe do an example of Guy-Luszak's law. So let's say I have a gas it's in a sealed container whose volume can't change. So whatever the volume is, I don't care. But let's say it's at 5.00 atmospheres pressure, and the temperature is, let's say, 20 degrees Celsius. Now, let's say I increase the temperature to 70 degrees Celsius. I'm using sig digs here, I'm just not saying them. What's the new pressure in the container? Obviously the pressure is going to be higher, but how much? Well, notice what I gave you is a P1, and a T1. You're looking for a P2, and this is your T2, right? So P over T. P1 over T1 equals P2 over T2. Now, scrolling down, I guess I should keep that on there, P1 was 5 atmospheres over T1. Now, don't forget, pressure can be in any units you like. We used atmospheres here. Temperature is, as long as you're consistent. If you decide you want to use, kilopascals, that's not going to work. You got to be consistent. But temperature has got to be in kelvins. There is no choice. So 20 plus 273 gives us 293 kelvins. Equals, P2 I'm looking for, and then the temperature is 70, so it looks like, 343 kelvins? And so just plug in and, cross multiply and solve, and you'll have your P2. Once again, I don't have a calculator sitting next to me, so I'm not going to do that, but it's easy enough to see that it's 5 times 343 divided by 293. And you'll get your P2, and it will be in atmospheres because that's what the original thing was in. So that's how you use Guy-Luszak's law. It's just the same as all the other gas laws. Now, I'm going to clear my smartboard here and start putting things together a little bit here. Notice Boyle's law. We had PV equal PV, equal to constant, right? Now, that constant involves other factors. What other factors? Temperature, and now we know number of moles. So, how does temperature factor into this? Well, Charles' law was V over T. So for the most part, PV over T is how you want to remember all this. Okay? So PV over T, if you're holding temperature constant, you can get rid of that and just get PV equals PV. That gave you Boyle's law, didn't it? If instead I'm holding pressure constant, you can get rid of that and get V over T, which is Charles' law. And if you're holding volume constant, get rid of that, and then P over T, you got Guy-Luszak's law. So this PV over T, if you just remember that, that pretty much ties in all the gas laws. Well, all three of those gas laws, Boyle, Charles, and Guy-Luszak. Okay? And all you got to remember is PV over T. And then just get rid of the one that's not changing. Keep the ones that are changing. And it'll give you the gas law you're working with. But now that also brings us to an interesting fact. What if everything's changing at once? Up until now, we only wanted to change one thing so we can figure out what was going on with each. But now that we know, we can change everything at once. I could change the pressure and the temperature and ask for the new volume. Okay, fine, then just nothing goes away. P1 V1 over T1 equals P2 V2 over T2. All right? By the way, if we throw Avogadro in there, number of moles goes on the bottom as well, because if you look back at Avogadro's law, that's how it fit in with volume. So really, just PV over NT is the way you remember all your gas laws. Okay, and then just leave out whatever is constant. For the moment, I'm going to get rid of that N because we often don't use it in this context, and build what we often call the combined gas law, which is that. It combines Boyle, Charles, and Guy-Luzak all into one gas law. Again, you can put down here an N1 and an N2 if you want to throw Avogadro in there as well. We often don't bother with that. Okay, so let's say I give you a gas, and it's at a pressure of 5 atmospheres. I'm going to even drop sig digs here because I'm really getting lazy and running a little low on time. And it's at a volume of, say, 100 milliliters. And it's at a temperature of, let me use Kelvin right off the bat. Let's say it's at a temperature of 200 kelvins. So I got a pressure of 5 atmospheres, a volume of 100 milliliters, and a temperature of 200 kelvins. Now, what if I change the pressure to 20 atmospheres? And I change the temperature to 400 kelvins. What's the new volume? Well, again, as I was saying the problem, I was plugging them in, and I'm picking simple, easy numbers here to work with too. So life is really, really easy here. You just plug in the pressures, volumes, temperatures, and then solve for the one unknown thing. It's really just doing Boyle's law and Charles' law and Guy-Luzak's all combined together. You could, instead of doing this, have first dealt with the pressures by themselves with Boyle's law, and then take that answer and adjust it for temperature using Charles' law. But this makes more sense just to do it all at once. It's like doing our mole problems all in one big, dimensional analysis thing rather than splitting them up. So now that I've got all that, I can start simplifying, right? So we got 500 over 200, since I don't have a calculator, I'm doing it by hand, I picked easy numbers, equals 20V2 over 400. I could have simplified that, I guess. So now, I'm going to reduce these zeros, So 5 times 40 is 200, equals 2 times 2 is 4V2. Again, use a calculator if you like. And now V2 equals 200 over 4 is, what, 50, right? Looks like we get a volume V2 of 50 milliliters. So I took my 100 milliliter volume, and now notice the pressure grew, and so that made the volume shrink. The temperature grew, which made the volume grow. So in this case, the temperature and the pressure are working against each other. One's trying to make the volume expand, the other's trying to make the volume shrink. But notice the temperature doubled, and the pressure changed by 4 times, so the pressure changed by more, so it won. It shrunk the volume down to 50 milliliters, and it makes sense. Okay, so again, you combine the gas laws all into one big glorious equation, PV over T. And in fact, again, you could do PV over NT and even throw Avogadro in there. And that's it for combining the gas laws. We'll play around with that a little bit more, and then I'll give you the grand unified ideal gas equation. And we're done for today.